Welcome back, everybody. Stand behind this line to be lit. I'm the moderator of this panel session, which I've just met all the panel members. I was going to do a few slides here to talk about a thing that I've been particularly interested in getting people involved in. So I'm probably going to spend my time talking about that. Unlike many of you here, I don't really have much of a medical background. I put myself in the category of friend of Anthony. A long time ago, he took a class of mine at Stanford and kind of opened my eyes in a lot of stuff in the healthcare area. I over the past several years have been working in this whole area people refer to as the Internet of Things. One of the things that has happened there is I've invested in a young company which has a bunch of my former Stanford students in it, to basically take these AI, deep learning, neural network technologies and bring it to the world of things, meaning learning from large amounts of data coming from things like wind turbines and combine harvesters and things like that. One of the things I think we've learned, and you guys probably already know, is that the game is being played really by bringing tons of data to this problem and tons of compute. And so if you can get a lot of data, you can improve accuracy, let's call it nearly linearly. So I've obviously started getting interested in the whole world of healthcare machines. So I had the opportunity, because I know the guys at Chalk, to try to understand, well, what are all the machines inside a hospital? I found it somewhat amusing that it took 3 months to get a list of the machines, and the only reason that I got the list was because they had to do a move into a new tower. So here's a Excel spreadsheet of the move. And what I was really surprised by at the end of the day was that out of about 1,000 machines in the hospital, only 16 of these were connected outside the hospital. And I started reflecting on that and pulled up this chart, which some of you may have seen, which is that the consumer internet that has transformed all our lives. If you go back in time, what you'll see is roughly in 1994, we hit about 1 million connected machines. And it was at that point in time that things like Netscape and Google, et cetera, came into existence. Obviously, if you were at 100,000 machines, who would care, right? So if you think about that, at 1 million machines, I did some back of the envelope, which is there's about 500 children's hospitals in the world. What if we could connect all of the machines in all the hospitals in all the world, all the children's hospitals? That would hit about 500,000. So it's a very interesting point in the curve. So about a month ago, I brought a group of people together, and Anthony helped do this as well. We brought some of the guys that make machines, so the Siemens of the world, Beckman, et cetera, together with some of my local technology friends, guys at Qualcomm, Nokia, guys in the backbone area like Tata, who you've already heard from. And so what we are in the process of doing is trying to design what we are calling a vertical internet for children's hospital things. So by and large, taking all the technologies that we already know how to bring to bear and focusing it directly on doing this, because I'll say at the end of the day, if we could tie all the machines in all these hospitals together, what we have seen in the consumer internet could vastly transform what is happening in our world. I'll end with this because some of my friends have asked me, well, what's the value prop, right? Why would you want to do this? So I happened to be with one of a very seasoned pediatric cardiologist the other day who said, well, I have to do a consultation. And I went, okay. So we went into the office. He sits down next to a tower PC. I go, when was the last time you saw one of those? And then he hits the button and opens up the tray. When was the last time you saw one of those? And then he takes a CD and he puts it in there, hits the button, and is now looking at an MRI scan. And I'm thinking, God, this is so primitive. So I know there's a lot of cool technology in front of us, but if we could just connect these machines, I think it'd make a major difference in how we think about computing in the healthcare world. If you're at all interested in this, please connect with Anthony or myself. I'd love to talk more about it. But my job here is also to bring the panel up. We have a very interesting group here for you to listen to, and I'm going to I don't have to hand him the clicker. I'm going to turn it over to Gary.
Spiritual hand. All right, so I told you that I was going to beg. Can you hear me? I feel like I need a mic. I guess this will work. That sounds much better. So I promised you in my opportunity to tweet yesterday that I was going to beg you for help, and that's true. But first I'm going to say how I would like to help. And then the kind of help I'd like to get there. So I ended my last presentation by talking about this metaphor, the difference between being driven by historical data versus predicting the future. So the paradigm that we're making a lot of progress on now, well, maybe we, not including me, but the field is making a lot of progress on right now, is collecting historical data and being better able to say, in circumstances like this, we've tried that. But I think the ultimate would be more like SimCity, where we actually model the patient using everything we know about a patient's records and everything we know about biology, automatically integrating the science of how different pathways work and how different tissues work and how different organs work, so that you could get to a situation where you have a patient that is unique and be able to predict what might work for them in a dynamical system. So what might work for them, what sequence of medications might work, how are things going to change over time. So I think this should at least be the aspiration of the field, is to try to model what's going on so that you have a simulation like we have in SimCity of the patient and you can predict the future. Stepping back a second, I don't think we can do this with deep learning. We've had a lot of discussion about deep learning, beyond deep learning, and so forth. I just want to review a few of the places where I think that deep learning is not really going to get the job done. One that I'll talk about in a second is resolving information that's perceptually ambiguous. So what deep learning really does is it classifies things. It's a perceptual classifier. I see a bunch of patterns and I have labels about what those things should be, and then I see some more and I say, which of those labels does it most look like? Well, that's just perceptual. It doesn't include the rest of cognition, of thinking about things by and large. There are exceptions to everything I'll say on this slide, and I can't see Jeremy out there, but we can have a fine discussion about those exceptions. But I think as a first approximation that we can think of deep learning as a classification system that doesn't work that well with perceptual ambiguity. It also doesn't work that well when we need very high levels of accuracy. So most of the demonstrations we have are things that are like 99% correct, and that sounds great, but if we're talking about medicine, the 1% error can be catastrophic. Rare diseases, another thing that I think deep learning is not very good at. So if we don't have a ton of data, deep learning is not usually the right technique. It's usually the right technique when we have millions or billions of examples. Again, Jeremy and I could have an interesting discussion about that. Knowledge integration that's individual to unique patients, I think, is again something deep learning is not particularly good. Modeling complex dynamics over time. What deep learning is really good at is looking at static images. You have a large collection of things that never changes. So we can discriminate cats and dogs because cats and dogs basically look the same now as they did 100,000 years ago, so there's not a lot, or at least 10,000 years ago or 5,000 years ago. So there's a lot of stability in the data over time. That may not be true, for example, if you have a new illness. Robust, high-quality natural language understanding is something that's way beyond deep learning or any other technique that we have. But we have to be realistic about that. So to get to my dream of automatically integrating the scientific literature, we have to have machines that can read. Deep learning is just too approximative to get there. And I guess automated scientific reasoning I just mentioned. So I just give you one example. I gave you this notion, this pie chart the other day, sort of standing in the way of perception, language, reasoning, analogy, common sense, and planning, and said, look, we can do some of that, namely perception, with the techniques that we have now, but not other pieces. And so on the top right, I have a picture which some of you will recognize from your introduction to psychology classes. It's kind of a classic picture, and what's interesting about that picture is one picture could mean two different things depending on the context. So if we had a lot of context about ducks, you would think it's a duck. If we had a lot of context about rabbits, you'd think it's a rabbit. One of the things I was hoping to learn here, and I hope some of you will still teach me, is what are the cases like that in medicine? So we have these tools that can read images but they're not going to be able to deal with the context in that way. And I'm guessing that if you're a radiologist or you're a pathologist and you see a particular pattern of pixels, you don't just look at those pixels in isolation, at least some of the time. Some of the time, you look at those pixels in the context of what the patient's history is and what you know about medicine in general. It's not a blind decision just based on the pixels alone. Those are the cases where we might need more cognition in the systems that we're building. And then another example I have is at the bottom, there's a dog there doing a bench press. Now, a deep learning system could identify the dog, and it could maybe identify the weights. It's probably not going to say, that's really weird. How did the dog get so ripped that it could do a bench press? But that's really what you should be doing in medicine, is saying, well, I've seen A and B before, but A and B together, that's telling me something. That's where I think we need more sophistication. So as an AGI researcher, someone trying to understand artificial general intelligence, I want to know, what are the problems where next generation AI could help? So we already know that we can do a lot of radiology and things like that with the current generation, but where can we push the limits? Where is that going to help us? Where is perception by itself not going to be enough? So in the spirit of the holidays, I have put up a wish list. I want to know what problem in cognitive medicine you would like solved, and where we would find, let me say that more slowly, in cognitive medicine, I've just made up a term here, in the medicine that isn't just pure perception, just looking at a diagram, just looking at a picture, but where you have to put together your knowledge as a physician. What are the problems like that you face in your domain? And where could one find relevant data to work on it? So if you have a suggestion, I'm a entrepreneur and scientist who's looking to get into this field. I'm trying to find the right puzzle. So send me an email, gary.marcus@icloud.com. I'd love your thoughts on cognitive medicine and how I might get into it and how I could help. Thank you very much.
Morning. I'd like to thank the organizers for inviting me to present our work on mixed reality and biomedicine at Children's Mercy. So we as human beings experience the world in 3 dimensions, but we use 2-dimensional monitors to do most of our analysis and communication about that work. So I'm going to talk a little bit about how we're exploring some technologies that we think can get it past that. One irony today is that I'll be talking about 3-dimensional visualization, but I'm still using flat screen monitors to show you our work. Some areas of opportunity for 3D visualization in biomedicine. So I'm trained as a molecular biologist. I did work with protein visualization, so I gravitate towards molecular structures, macromolecular structures in which you can visualize DNA and protein complexes, protein-protein complexes. There's a growing library of larger structures generated through cryomicroscopy and others that are 3-dimensional visualizations. If you're a 3-dimensional thinker, there are countless opportunities in what's referred to as the built environment. So I really enjoy collaborating with architects, and I don't know if that's a field that's really been tapped very heavily, but healthcare happens in physical structures, and there are aspects of those structures that can impact the process of healthcare delivery. Anatomy. So we've already seen some great examples of using these technologies to teach anatomy. Surgical training, there was a great HoloLens presentation earlier in the conference. Surgical planning. There are some interesting uses of virtual and mixed reality to help providers identify patient veins. And then there's also a body of growing work in using these technologies as an intervention. And we've heard brief mentions of using technologies such as these for pain management. It's helped me to really parse through what is virtual reality versus augmented reality versus mixed reality. So briefly, virtual reality is completely immersive, and probably the most familiar example is the Oculus Rift, as well as the visors that you can make by inserting your cell phone. For me, I'm prone to motion sickness, so there's a growing body of evidence that those can induce nausea and dizziness. So that technology is not for everybody. Most of those technologies have to be tethered by a cord to a computer or a phone. But as shown in the example here, there's one nice example where for mindfulness, they created an immersive example. Augmented reality blends the real world with the digital world. And many augmented reality examples use your cell phone camera. So Pokemon Go is one. Google Glass was an early venture into that area. And certainly that has a lot of use. Mixed reality, I would encourage you to consider as a subset of augmented reality. Some of the key differences are that mixed reality is aware of the environment. So it uses a technology called surface mapping. So this is my somewhat messy office. Above is what I see with my eyes. Below is what the technology that I'm using sees as a surface map. So the device maps the entire room, identifies flat surfaces, and generates a kind of spooky looking file. But you can see the similarities where my table, chairs, computer, storage, you can really see the connections between the two. So mixed reality systems use that so that you can pin applications to structures. Some of them also integrate persistence of settings, so when I relaunch the application, it's exactly where I left it before. And so those are some distinctions between mixed reality and augmented reality. So the Microsoft HoloLens is the technology that we've emphasized. It's an untethered device. It's a complete standalone computing platform. It's Windows 10 based. It has Wi-Fi connections so that you can receive real-time data from APIs, 3D audio, surface mapping. It uses both voice and gesture commands, and you'll see some examples of those in just a moment. And then you can download example apps from the Microsoft Store directly onto the device. We've put a focus on developing what I think of as data pipelines. So one data pipeline that we've developed is the process of taking a three-dimensional structure and loading it into the HoloLens. Another data pipeline is taking a patient imaging visualization from a CT scan, for example, and migrating that into the HoloLens. We're also starting to develop a software toolkit that we'll be making available to the public next year so that some of the basic controls that you'll see in our examples will be available for anybody who wants to integrate them into your augmented and mixed reality projects. So the first example that I'll share, this is the protein structure of a bacterial toxin, the one that I studied eons ago in graduate school. And you'll see that with the mixed reality visualization, you can peer into the structure, you can rotate it using gestures, and the controls that we developed allow you to resize it and with the simple gesture-based interactions. And then you can remove the surface view, and that's something that's very difficult to do, to jump back and forth in a two-dimensional visualization. You can stick your head inside the protein and look around at the ribbon diagram while it's also presented in the surface diagram. Another example is a macromolecule. So I enjoy showing this to engineers because if they saw that, they would think it's a motor, but it's actually a bacterial flagellum. And so here, again, using touch, you're rotating the motor, and then you can hide and show different parts of the flagellum with simple tap-based interactions. So again, you can see this common library of controls becomes very useful because we can just through this data pipeline load any structure into this kind of core application. And then the last example is an anatomical structure. So this is a skull. And if you want to get into this, I would recommend that you actually start with the NIH 3D print exchange so that you can avoid any IRB issues, but work with actual human structures. So that's one recommendation that I would share with any of you who want to really pursue this. But this shows a skull, and again, you can rotate it, and the hide feature becomes especially useful because through a simple tap, you can hide the skull features, and then you can really focus on visualizing the vessels. And for the clinicians in the room, you might notice that this patient had an aneurysm developing, and so again, that's a potentially useful example. And there was a nice discussion yesterday of working with a patient to show her aneurysm, so this would take that a step further. Other examples, the built environment, again, the example I'll show in just a second uses the Google Earth, but a three-dimensional visualization pinned to the table in my office. There are also examples. There's a tutorial about CRISPR that does a very nice job of explaining that technology. And then there's an application for three-dimensional visualization of pathway graphing. But this example is from Google Earth. This is Children's Mercy Hospital viewed from Google Earth. And again, using the gesture controls, you're able to zoom in, rotate. I'm not showing it here, but it actually can overlay traffic data. So for some cities that have heavy traffic patterns, you can overlay data sources dynamically into these environments. So to wrap up, there are a couple of mixed reality development models. One is to develop an application. This would be using gaming design concepts. So if you want to get into this, I strongly recommend learning the Unity game development engine. That's the platform that's used most heavily for these. The applications can be used for training and other fairly static, fixed, scripted examples, although you can connect APIs. It's not real clear on the bottom, but there's a newsfeed demo app that just draws in real-time news feeds from every little window there is a different news feed from CNN. And then the model that we've focused on is more of the pipeline, where we want to take specific visualizations and pull them through this process. So to conclude, there are some roles for AI. Cortana is embedded within the HoloLens. The next version will have even more sophisticated AI. I also think there's a role for automating the annotation pipeline and generating those dynamic data feeds. So I'd like to thank you. If you're a fan of The Good Doctor, there was an episode recently where they demonstrated the potential of this technology for surgical planning. So thank you very much.
Good morning. So I think I've met most people here, or at least maybe you saw my first talk. So my name's Sean Lane. I'm the CEO and founder of Crosschecks. We're the people who work with Olive. So if you've seen Olive, that's us. I want to talk about 4 concepts today. And I'm going to start with a concept that we call the ASOC. So as some of you may know, I spent a lot of my career in the intelligence community. I worked at NSA, and I spent a lot of time working in operations centers. So we worked in fusion centers, tactical operations centers, joint operation centers. So whenever we wanted to really focus on something and take it very seriously, we would all gather in one room, multidiscipline, people from all parts of the military and the intelligence community. We'd put big screens up on the wall, and we'd focus on that task. We'd bring in all the data. It would be 24/7, unflinching. We would look at it. We would think about it. We would solve problems. And I really like that model. Working in an operations center is like nothing else. You get the opportunity to really focus on a problem. So the ASOC is the Automation Support Operations Center. As we started talking to health systems and healthcare organizations across the country, we found that people had notions that they wanted automation and artificial intelligence. They weren't sure how to operationalize it, and they didn't yet have an enterprise kind of strategy around it. So the ASOC is a way for them to focus completely on automation and artificial intelligence. So we set up these automation support operations centers in hospitals now with a full focus on things that could be automated and or where artificial intelligence could be introduced. In the ASOC, we usually staff it with first an operations analyst. The operation analyst goes through the entire health system, finds what we call CPAs, candidate processes for automation, also places where we can use artificial intelligence to improve either clinical experiences or administrative experiences. And then we go through a methodology to rack and stack all those, and then engineers build that tool, we deliver it, and an intelligence analyst is monitoring constantly the ROI and impact of automation and artificial intelligence throughout the organization. So it's a really interesting model for making artificial intelligence and automation an infrastructure within health systems. So speaking of infrastructure, when we started looking at artificial intelligence in the beginning, we didn't know how to monetize it. There wasn't a good pricing model. We've adopted a lot of the SaaS pricing models, and there's a license fee, a maintenance fee, a monthly ARR, typical software and SaaS deployments. But we didn't think that was sufficient for AI. When we started, we sold it by the AI unit. And what is an AI unit? Well, it's whatever we made it up to be. So it'd be one AI unit costs X dollars. But that, again, we didn't quite hit the nail on the head. What we ended up moving to is what we call a kilowatt hour. So a kilowatt hour is about 1,000 actions of some kind of AI device or bot. And a kilowatt hour works a lot like a kilowatt hour of electricity. So if you can imagine your home, which is the electricity is measured in your kilowatt hour consumption, for an organization, your AI deployment is measured in kilowatt hour consumption. So basically your meter runs. If you're doing basic automation, like let's say you're manipulating the user interface or macroing something essentially, you're going to have that meter run pretty slowly, like if you were to plug a nightlight into your wall at home. If you're doing convolutional neural nets, dynamic neural nets, you're actually using a deep amount of AI in decision making for a bot, then that meter is going to run a little faster. So it's going to be like plugging an air conditioner or a refrigerator into your wall at home. So that's the model that we use, the kilowatt hour. Now, the thing about the kilowatt hour is that we don't want to be the only ones who use it. We actually think it's a really good way to monetize and a business model around artificial intelligence. We would love to see other people adopt it. We want to share in that because we think that this could be a really good way to price it moving forward. So the next thing I want to share, and this is not to be confused with MIT's Mimic database, is a platform that we use internally called Mimic. When we started to build Olive, what we realized is that some of the automation tools that exist out there, some of the RPA tools, as Nardo talked about yesterday, aren't really sufficient. They didn't really have all the capabilities that we needed. Computer vision was relatively lacking. Nothing integrated Tesseract 4, which was like the latest and greatest of computer vision that was publicly available. We couldn't run our own conv nets or convolutional neural nets. And then we weren't able to really manipulate at the VDI level or the DLL level with native applications. So we built our own tool upon which we then built Olive. So you've heard of Olive. You probably haven't heard of our version of Mimic, which is our internal platform upon which we build Olive. Now to do this, and as a company, we had to think about, okay, how do you scale this, right? Am I gonna have to hire 1,400 engineers that are gonna basically build automations for everybody in every hospital and every healthcare organization across the country? Or can we make Mimic so easy that any human could build a bot? So we decided to make Mimic so easy that any human could build a bot. So think about it like Weebly or Wix or Squarespace, how anybody can build a website nowadays. It's very, very easy. It's straightforward. You don't have to be an engineer. You don't have to be a developer. So the cool thing about Mimic is that when we do release it to the world, right now it's just our team that's using it, and we haven't decided to give it to anyone else yet. But when we do, anybody in your organization, anybody across the board will be able to build an AI bot. So this is kind of a preview of what's to come in the future. And on that theme of previewing what's to come in the future, I want to talk about what we call AAA internally at Crosschecks. And this is a concept that we're super excited about. Automation autonomously. So a little bit of a mouthful, but the whole idea here is that we don't need to discover processes that need to be automated. We don't need to find things. We can allow the machine to find them for us. And we don't need to have an engineer build the automation. We can allow the machine to build the automation itself. So AAA, the way to think about it and how it manifests itself is basically something at the operating system level. And let's say your enterprise has 10,000 machines. Imagine something on 10,000 machines, 10,000 desktops, workstations, that's constantly monitoring every single thing the human that is on that system is doing. Every click, every page view, everything. And after watching and learning and listening for maybe a week or a month, the bot realizes what kind of things are repetitive, what kind of things are mundane, what kind of things the bot can take over. And the bot automatically builds that automation, and all the human has to say is, yes, go ahead and start doing that job from this point forward. So that's kind of where we want to take the future. We're really excited about that future because it allows us to scale. If you remember, if you were at my kind of first talk, one of the concepts that we think is super important is this idea of scaling humans. We want to get more out of our human workforce. Scaling humans is about working at the top of your license, as people say. It's about allowing humans not to be the routers in healthcare anymore. I really appreciated your talk earlier about how we need to build this children's hospitals, like a network, because I do think that there's an element of internet missing in healthcare. A lot of the themes this morning have been how to share information, how to connect everything together. And we've always been focused on kind of the homogenization of APIs in the back end to bring everything together, creating a universal data model. But what I think that we need to bring on board to create this internet is kind of a layer 9 AI bot router layer, where there are AI bots that perform the jobs of routers between health systems. So imagine an AI bot on one health system and another able to access the system, able to get to the data, and able to share data across the AI bots to other AI bots. So it's just something to think about in the future. These things aren't, from the Mimic side, it's not released, and AAA is not built, and it's not out yet, but there are things that we are thinking about and working on. So thank you very much for your time.
So good morning, everybody. I'm going to talk about, find the right, which is the great one here. Oh, it's the big green button, good user interface, which is actually a good jumping off point. So for the clinicians in the room, you all love using your EMR, right? I don't even have to turn the lights on to know there's no hands up. It's a huge challenge for folks. And so, but what I'm going to talk about is, this is a framework I use to talk about people when they say, well, what are you guys doing in AI in medicine? And there's lots of things you could be doing. And a lot of the conference we've spent talking about some of the things on the right-hand side of how do you build predictive models and those kind of things. Some of the automation things that you just heard about, critical things. Lots of excitement over cognitive interactions, whether that's speech and video and so on. But I'm mostly going to talk in the next bit about data extraction and how we better leverage sensors in the care environment to make the clinician's task easier. And this all grew out of a simple request I had for my team, and that is I want a doctor to walk in the room, take care of the patient, and walk out. I don't want him to touch a mouse or a keyboard. And we're certainly not there yet, but we're taking some steps down the road. And to do that, we've instrumented examination rooms. This is actually a Healthy Clinic, which is the family practice that provides care for Cerner Associates in Kansas City. And just examples of the ways that the exam room might be instrumented. The doors have switches, so we know when the patient went into the bathroom to change, when they came back out because the door opened and closed. We have 3D depth sensors installed at various strategic locations in the room to help us see the human interaction that's happening. I'm not going to talk about it today, but the EMR and the logs and the kind of things that you were just hearing about in terms of understanding what's happening with the process can be critical bits and so on. But also the person and the devices themselves, understanding what the clinician is doing. Are they up walking around or are they sitting down? Which clinician is in the room? And then our traditional devices are increasingly can be instrumented. So the otoscope that I use, and I'm a general internist, practiced for 30 years in an academic medical center. These devices that we use every day can increasingly be instrumented. So my otoscope is Bluetooth enabled, and I can be grabbing images from that as they're being used during the interaction with the patient. And one of the things I think is really important here is that we as clinicians are trained to observe patients, to try to interpret what we observe in consistent fashions, and then to leverage that data. Now, everybody interprets edema exactly the same way, right? 4 plus edema, 2, there's no 4, there's all these arguments and discussion. The variation in how we interpret auscultation of the cardiac sounds is profound, whether you're a cardiologist or a primary care doc or a pediatric intensivist. None of us will agree on the details. It's not quite true, but it's a very poorly consistent test. But one of the beauties of leveraging sensors and the AIs that can interpret that data is that we begin to create, number one, consistent data that can feed into the algorithms that subsequently are downstream. Second, they're continuously improvable. I was chatting with somebody this morning about physicians' interpretations of ultrasound and some of the challenges that the device maker was having, in the sense that people would come out of their training course and they were great. they were like, I think you said 20% down at 1 year, 50% down at 2 years, and it continued to tail off from there. And you'd have to bring them back in and retrain them and so on to get the full value. You don't have that problem, obviously, with the machine interpretation of things. So I think the ability to achieve human or superhuman performance in various aspects becomes critically important. So what are some of the concrete things? And you're going to hear an emphasis here on pragmatic sorts of things. I'm very interested in what is the state of the possible, because I'm interested in getting care improved, not just in publishing papers or getting cool research projects. So first of all, things like the clinician, we may instrument their phone. What we find out is 30% of docs aren't carrying their phone around in the room, especially women. There's no convenient way to do it. We may use other devices, like this is a little Arduino device that we've embedded accelerometers and other sensors in so that we can track, is the clinician sitting, where are they going, what kind of activity, and that helps us know about when and where to provide feedback. In the examination room, I mentioned the 3D depth cameras, and I'm going to talk a little bit about that and how we're deriving from that in a staged fashion, understanding of the human-to-human interactions that are going on. There are simple things to do with sound, and I'm going to talk about speech as well in a minute, but even simple things with sound, everybody in here probably realizes, we let patients talk for about 14 seconds on average before we interrupt them. The dynamics, the cadence, the amount of time that is spent in conversation can give you clues to the patient-physician interaction. And then you can do more, as I'll talk about in a second. So just to make this kind of concrete, here's a different exam room and another one of our campuses and the clinics. And down at the bottom, labeled number 2 here is one of those depth sensors. Over on the left, labeled number 1 is a depth sensor. And part of the point here is just there's physics challenges that happen. For example, the depth sensors we started with, Microsoft Kinect, have a very wide range of view. But even in these limited spaces, it's hard to cover the whole space, even with 2 sensors. You need 2 sensors because people obscure things. When people designed the Kinect, the idea was I'm standing in front of the sensor playing my game, there's nothing in the way. In the exam room, people are walking around, they're obscuring each other and so on, so you need multiple sensors to make sense out of it. We also chose this kind of approach in part because in healthcare we have a lot of the privacy issues that we may not run into in other areas. So, for example, people really don't want a picture of their pelvic exam being processed somewhere. So the capacity locally, without having an actual image involved, turn these into stick figures, if you will, give patients a lot of comfort in our early development and testing. They were like, okay, I'm all right seeing stick figures like this. I know what's being recorded. But that also leads us to do a lot of the algorithm application more at a local level. Rather than applying the algorithm in the cloud somewhere, certain of the processing we're doing locally in order to preserve privacy, including the speech. And so then so we have sort of these stacked or staged sets of models. So as most of you know, the Kinect probably uses a set of hierarchical models and Bayesian networks to create those stick figures. There's another layer of networks on top of that do the human activity recognition, which is some really fun and interesting stuff over time. And then speech, I mentioned earlier, and obviously a lot of work been done on conversational speech, and you see the various announcements from folks, we're better than you, and we're now better than humans, and so on. And then the ability with NLP to turn that into structured data. But again, when you get to the pragmatics, it gets really interesting. This is a simple little graph of the findings that we had from conversational speech, real patient-physician interactions happening in an exam room, 2 different microphones, one a studio quality omnidirectional microphone over on the left, and the other a array microphone built into the Kinect on the right. And look at the difference between the performance of algorithms based on which microphone you chose. We were really surprised to see that extensive of an interaction, and just drives home how some of these pragmatic issues fix things. The other thing I'll point out on this is that the performance of conversational speech, which again, some of these engines arguably are 93, 94% in the telephone data sets, which are sort of the benchmark for conversational speech, are 50, 60% in conversational healthcare. And partly our conversations are different, nobody's surprised, so there's work to be done to extend these models. And then as an example, I mentioned the otoscope images as a concrete example of capturing devices. And here we start out again being very pragmatic. The first algorithm we used was Google image search. So we took the image, fed it into Google image search, and sure enough, we came out with a whole bunch of good matches. We're able to kind of cheat and use that in the early versions. Now we have sort of a full-fledged recognition, the AWS service-based image categorization set of tools built around that. And what this lets you do is start then at the end of the day to pull all of those pieces together. And so part of the thing that I think is important here is, we're taking things that others have done, obviously, whether it's Baidu's speech recognition or other tools for image recognition and so on. But our ultimate goal is to pull all of those pieces together in order to do something really useful. So in this kind of trivial example, the pediatrician's examining the child's ear here. And first of all, from the EMR, we know some stuff, right? We know some context. The patient's 7 years old, their fever, their temperature when the nurse took it a little bit earlier in the encounter was 101. They may be complaining about ear pain. And then the second thing we know based on the depth camera is at a point in time, and for a period of time, we know that the clinician's hands were adjacent to the patient's right ear, right? At 12:22 p.m., the patient's hands were adjacent to the clinician's hands were adjacent to the patient's right ear. And then the provider says, wow, this ear looks infected. That's interpreted, and you get some data about ear and infected. And then the image analysis lets us know that the tympanic membrane is bulging and that the ear is erythematous. And from there, it's sort of child's play to say, okay, great, patient's got acute otitis media, and you can generate the appropriate documentation to support that. So work in progress, but a lot of fun to be had.
So thank you, everybody. We'll let this run a little bit, but I'll throw a question over here to Mark. I've seen a little bit of this work in the whole AR, VR space. And one of the things that some people are saying is that AR has a lot of potential, but these glasses things, they're still not, they're under, they can't build big enough batteries for them, they're hot, so we're a long way away from actually being able to use this because our devices aren't really there. So curious what you think about that.
I was especially impressed with how, for first release, how stable the HoloLens Developer Edition has been. No issues really in our experience with the battery life. The network connectivity is probably more, occasional issues with that, but that's more of a reflection on our network rather than the device. So we really have been impressed with how stable it has been and how, the data pipeline that I described, we can conceivably bring a structure from raw CT to the HoloLens in an hour or two. And that's with annotation, migration through the multiple platforms. So I think we're very promising. What we're not doing is assuming that it's beneficial, so we're starting to do actual research, comparative studies with providers and surveys and to evaluate, because it's always tempting with a visually striking technology to assume that it makes things better, but we're being very careful about doing human factors analysis and so forth.
Actually, there's a Cerner question. Mark, I'll just throw a question over to you about Cerner. I'm curious, you have the IoT thing in there. So to what extent are you guys looking at the connection of these machines themselves, the MRI scanners, gene sequencers, blood analyzers? I mean, go through the list.
No, really critical part of things. And part of Cerner's platform, not trying to be commercial here, but to answer the question, is to connecting those devices and the data that drive them, whether those are ICU monitors or Fitbits or is a foundational part of the platform. So making that data in real time available and flowing so that it can be leveraged, and then connecting that across clients and patients, clients for us being hospitals and health plans, et cetera, as they want to connect the data across those enterprises.
I saw one go by here. Sean, when do you plan to open Mimic for external developers?
Well, we've thought a lot about this. We built Mimic for ourselves, so it is a beautiful platform, but there's still some work to be done in order for it to be kind of commercially available. The truth is there are a couple beta users that we're opening it up to right now that are other organizations who have the team and the capabilities to start building bots on that platform. But I haven't decided yet, to be honest, when we're going to release it. But if we want to achieve having 10 million bots in the healthcare workforce, then I think we need to.
Gary, I'm curious by the nature of your presentation, because I've been spending time in many other industries other than healthcare, and I'm guessing you have too. Do you think the opportunity is greater in healthcare, the barriers are more difficult, or versus other, let's call it other verticals?
I think I want to do it because I think it's important. I think the barriers are a lot higher than some other things that I could be working on. So, for example, video understanding is something that I could work on, and there's lots of ways in which you could sell more advertisements by making better video understanding. But I guess I don't want to spend the next 5 or 10 years of my life selling advertisements. I want to do something that's important. So I hope I can wade through all those obstacles. I've certainly learned a lot about them in the last few days, but I think the value, maybe not in dollars, but for humanity is a lot greater.
No disagreement. Sean, you're supposed to release it on Christmas morning. Okay. I think you just need to price it.
Like next year, Christmas morning?
Yeah.
A Christmas morning, some year.
Oh, good. We can pick on EHR. Hey, is remote monitoring or capture and integration of data from non-clinical sites finding its way into that antique EHR system? That was my comment.
One of those trick questions. No, absolutely. And data, whether it's from Fitbit, scales in the home, peak flow meters. In fact, Children's Hospital here in Orange County is doing work with this, bringing data from peak flow meters being used in the home into the care process are all critical parts of delivering care. And I think this whole Internet of Things is continuing to explode in many ways. The number of life sciences companies that are embedding devices and monitoring into therapies now is surprising me. So if you use a metered dose inhaler, there are devices and companies that can now tell me what location geographically, which user, how many puffs, pressures that were administered that suggest the efficacy of the inhalation, all streaming in real time from those medication devices. So I think that's going to continue to expand. And I think the challenge there is more in learning, and this is great for this group to take on as a challenge. What does that data mean? One of the first projects I did, for example, was looking at ventricular tachycardia in healthy 20-year-olds. Because in drug trials where we'd lock people up for a month and give them experimental drugs, we'd see VT and 3-5 beat runs of VT, and what the heck does that mean? Or what does your blood pressure 180 over 132 on Thursday afternoon when you're sitting at your desk mean? And so I think we got a lot of work there and how to take advantage of that data and how to interpret it and what to use it for.
Can I add something to that really quickly? I mean, aside from the IoT and kind of quantified self devices out there producing data, Olive actually started as an idea of how to support a DSRIP PPS, if you're familiar with that program, Medicaid Accountable Care Organization, and they wanted to know when their patient checked into a homeless shelter. So it was really difficult because you have the system used at the homeless shelter that logs everybody who comes in, and then you have the EHR. Obviously, those two things don't connect, so we just put Olive can log into each system and see when the patient comes in and to report it back in the other system. So there's a way to do kind of data outside of the EHR and bring it into the EHR environment in an other than IoT scenario as well.
Very cool. Let me see. What's a good last question? 27 seconds. We keep on schedule, so I'd like to thank all the panelists for taking the time to do this and for all of you for listening. So, cool.